in this video, we're going to take a look at the end behavior of polynomials. Polynomials are just finite sums of power functions. So power functions are polynomials that happen to have just one term in them. Let's suppose we wanted to take a look at the limit as x goes to infinity of 3x to the fourth minus 5x cubed minus 2x squared minus 3x plus 1. Okay. So this is a fourth degree polynomial. Now, because each of these terms is just a power function, we know how to take the limit as x goes to infinity of each term. However, in this case, being able to do that isn't going to help us to see where the entire thing goes. Because notice, we're going off to infinity, so x to the fourth would be going to infinity. A positive multiple of that is still going to infinity. Then we're subtracting 5x cubed. Now, I'm going to just view that negative sign as being part of this term. I'm going to view that as plus a negative 5x cubed. That negative is going to make that piece go off to negative infinity. Negative 2x squared is going to negative infinity. Negative 3x is going to negative infinity. And 1 is very content being 1. So that's just going to 1. So here I've used my arrow notation to say where each term is going. Notice I cannot apply the theorem that says it's okay to take the limits first and then do the arithmetic, because arithmetic is only defined for finite numbers. So it would be wrong to say, oh, this is just infinity minus infinity minus infinity minus infinity plus 1, because we can't do arithmetic with infinity and negative infinity. Okay. You might look at this and say, well, look, I've got 3 pieces that want to go to negative infinity and only one that goes to positive infinity, so maybe these pieces win. And if all power functions were treated equally, that might be the democratic decision to make. But math is not democracy, and not all power functions are equal. Okay. Here's the basic idea. Okay. The bigger the power is, the faster that function is going to be doing whatever it's doing. So we saw, for example, when we were graphing x squared, and then x to the fourth, I'll graph x to the fourth in red here. Okay. X to the fourth is ultimately much, much bigger than x squared. Okay. So I want to imagine this as we've got these 5 functions here that are the individual terms of this polynomial, and they're sort of having a tug of war. And this piece right here is saying, hey, I think we should go this way. Let's go off towards positive infinity. And this piece here is saying, you know what, I've heard that negative infinity is a nicer place to go. I'd like to go there. But that piece, even though it's getting really, really big in the negative direction, it's much, much smaller than this piece is. Okay. This piece is going to agree with this piece. So this piece is trying to go that way. This piece is going to agree. So that piece says, yes, I've heard that negative infinity is a nice place. I think we should go there too. This piece, that's going to agree as well. That'll lend a hand in this tug of war and say, let's go off to negative infinity. And then we've got this piece, which is kind of going to lose. This piece, I'm going to just put in the middle, because these guys want to go to the right and these guys want to go to the left. This piece right here is saying, I'm very happy being right here. Can we please stay? I don't like change. All right, now I said this was like a tug of war, so I'm going to draw in the rope. So here they're holding the rope. And this guy's trying to pull things this way. And these little guys are saying, no, 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 please, let's go this way. And this poor little guy is saying, I want to stay here. Who's going to win? Yes, the big guy is going to win. Because what's happening is this term is ultimately so much bigger than these other pieces that even if they're really, really big And ultimately, these guys are really, really big. Comparably speaking, they're really, really small. Just to see this with numbers instead of pictures. If x is 1 million, now I think of 1 million as being a fairly big number, okay? Compared to infinity, it's minuscule, but I think of that as being fairly big. Now, x squared would be 1 followed by, instead of 6 zeros, 12 zeros. So let's see, that's thousands, millions, billions. X squared is 1 trillion. X cubed, now I'm going to have 3 times as many zeros. So that's 1 followed by 18 zeros. And x to the 4th is going to be 1 followed by 24 zeros. Now, I was saying I thought of 1 million as kind of big. Compared to 1 million to the 4th, it's minuscule. Okay? So, what's happening is that the biggest power, which we call the lead term, is going to dominate. Okay. So, if I want to take the limit of this whole thing, I can say that's going to be the same as the limit as x goes to infinity of 3x to the 4th. And the reason here is that as x goes to infinity or x goes to negative infinity. Okay. Now that's important. This is only applying to the end behavior. For values in the middle, these can be very important. For example, if x is 0, that kills off all of these terms. 1 is very happy because it gets to be right where it wants to be at 1. Okay. But as x goes to infinity or x goes to negative infinity, we say polynomials are dominated by their lead terms. Okay. Now, the lead term is the one with the biggest power. That's important. Here, the lead term happens to be the one that's written first. That's because it's often convenient to write polynomials in descending order. So we go from the biggest power on down to the smallest power. So the powers go 4, 3, 2, 1, and a constant term basically is some x to the zeros, because x to the 0 would be 1. Okay. But polynomials don't have to be written in descending order. So the lead term is just the one that has the biggest exponent. Okay. And this is a perfectly acceptable way of evaluating this limit. And I can say, oh, okay, that's an even power. Whether we're going to infinity or negative infinity, it would be positive. And I'm scaling it by a positive number, so this is going to be infinity. Okay. So we can just look at the lead term. Now, I gave you a fairly informal explanation of why that works. I can show you a little bit more formally. Here. If I'm looking at this and saying it's the limit as x goes to infinity, now the biggest power here is x to the 4th. What I'm going to do is I'm going to factor out x to the 4th from every single term. Now, if I do that here, what's left over is a 3 minus, I'm going to just write this out, 5x cubed over x to the 4th. If I'm factoring out an x to the 4th, I'm basically dividing by the x to the 4th. So, minus 2x squared over x to the 4th minus 3x over x to the 4th plus 1 over x to the 4th. Okay, excellent. So this becomes the limit as x goes to infinity of x to the 4th times 3 minus 5 over x minus 2 over x squared minus 3 over x cubed plus 1 over x to the 4th. Now, for evaluating these limits, I want to just talk through this using some common sense. Then we'll come back. There's actually a theorem that formally tells us what the result is here. But what we've got is these fractions that are getting really, really big in the denominators. I know the denominators are going off to infinity. So here it's like I've got 5, and I'm dividing by something big. Here I've got 2, and I'm dividing by something even bigger. 3, or -3, and I'm dividing by something even bigger. I'm sorry, there shouldn't be a 3 on the bottom there. It should just be x cubed. Okay. And 1 divided by something really, really big. Well, what happens when you divide by something really, really big? You get something really, really small. This is what I like to think of as the chocolate cake principle. And it's very important that it's chocolate cake because I like chocolate cake. So if I'm thinking about chocolate cake, I care about it, so I'm going to remember it. If it was lemon cake, I might not care so much, so I might forget the math rule. Okay. But imagine that I have here a chocolate cake, and I decide not to share. I get to eat the entire chocolate cake. I'm happy. Now, I might decide to share this chocolate cake with my best friend. That's dividing the chocolate cake in 2. I still get half of the chocolate cake. I'm okay with that. That's a decent thing. I decide to share my chocolate cake with all the students, not just in this class, but all the students at Saddleback. Oh, I'm not getting to eat very much chocolate cake. I'm getting crumbs. So when you divide by something big, you get something small. Okay. So this piece is going to 0, this piece is going to 0, this piece is going to 0, and that piece is going to 0. Which means the entire thing in the brackets here, that whole thing is going to 3. Because it's going to 3 minus 0 minus 0 minus 0 plus 0, which is 3. This piece is going off to infinity. It's an even power, and we're going to infinity. It's going to infinity. Now, I still can't apply my rule of limits that allows me to evaluate limits individually and then do the arithmetic, because this piece is not going to a finite number. Infinity times 3 is nonsense, and if you literally write it, that is a mathematical atrocity because you are treating something that isn't a number like a number. We will not do that. But we can use some common sense. I can say, I've got something that's big and positive. I'm going to multiply it by something that's close to 3. The size of this number is only going to affect how fast this thing gets big. What I'm looking at is the sign of the number. If it's negative, it's going to reverse the behavior. If it's positive, it's going to preserve it. So this whole thing is going off to infinity. So this is still a little bit informal because I'm using my arrow notation here, but that's another way of justifying that we can just look at the lead term. Okay. I'm totally fine as you're working with the limits of polynomials as x goes to infinity and negative infinity if you simply write that you're going to take the limit of the lead term and do that. But if you prefer to factor things out this way, that's certainly acceptable, and I wanted to show you that option. Okay, in the next video, I'm going to give you the theorem in the book that formally justifies us saying that these things are 0. I think we probably have it based on the chocolate cake principle, but there's a more formal mathematical theorem to give us that result.